Welcome to our deep dive into electromagnetic induction. This fascinating phenomenon is at the heart of how generators and transformers operate, powering much of our modern world. Today we'll explore what electromagnetic induction is, why it's so important, and how it's harnessed in everyday technology. Whether you're curious about how electricity is generated or how it's efficiently transported across vast distances, understanding electromagnetic induction is key. Let's begin by uncovering the basic principles behind this essential concept and set the stage for a journey through the science that keeps our lights on and our devices running. Story of electromagnetic induction begins with Michael Faraday, a pioneering scientist in the 19th century. Faraday discovered that moving a magnet near a coil of wire could generate an electric current. This breakthrough experiment laid the foundation for modern electrical engineering. Faraday's law of induction tells us that a changing magnetic field within a closed loop induces a voltage or electromotive force in the wire. This simple yet powerful idea is the cornerstone of how generators and transformers work. Let's see how this principle is applied in real-world devices. Grasp electromagnetic induction. We first need to understand magnetic fields. Every magnet creates an invisible field around it, influencing nearby objects. When a conductor like a copper wire moves through this field, or when the field itself changes, it causes electrons in the wire to move. This movement of electrons is what we call electric current. The interaction between magnetic fields and conductors is the basis for generating electricity in power plants and for the operation of many electrical devices. Faraday's law of electromagnetic induction states that the induced voltage in a circuit is proportional to the rate of change of the magnetic flux through the circuit. In simpler terms, the faster the magnetic field changes, the greater the voltage produced. This law is fundamental to the operation of both generators and transformers. It explains why spinning a coil faster in a generator produces more electricity, and why transformers can step voltage up or down depending on how quickly the magnetic field changes between coils. Generator is a device that converts mechanical energy into electrical energy using electromagnetic induction. When you spin a coil of wire inside a magnetic field or move a magnet near a coil, you create a flow of electrons and electric current. Generators are found in power plants, wind turbines, and even portable backup units. They are essential for producing the electricity that powers our homes, businesses, and industry. Let's look at the main components and how they work together to generate electricity. Generators have several key parts: the rotor, which spins, the stator, which stays still, and the magnetic field, which can come from permanent magnets or electromagnets. As the rotor turns within the stator, it changes the magnetic field through the coils of wire, inducing a current. The design ensures that as long as there's motion, electricity is produced. This simple yet effective mechanism is the backbone of our electrical infrastructure. When the rotor spins, it causes the magnetic field to move relative to the coils of wire in the stator. This movement changes the magnetic flux through the coils, and according to Faraday's law, this change induces a voltage. The faster the rotor spins, the greater the voltage and current produced. This is why power plants use turbines powered by steam, water, or wind to keep generators spinning at high speeds. There are various types of generators, including AC alternating current and DC direct current generators. AC generators, also known as alternators, are most common in power plants because they efficiently transmit electricity over long distances. DC generators are used in specialized applications like battery charging. Each type uses the same basic principle of electromagnetic induction, but differs in how the current is collected and used. AC generators produce a current that reverses direction periodically, while DC generators produce a steady one-way current. The choice between AC and DC depends on the application. AC is ideal for large-scale power distribution, while DC is better for small-scale or portable devices. Both rely on electromagnetic induction, but their internal designs differ in how they collect and manage the generated electricity. Generators are everywhere, from massive hydroelectric dams to portable units for camping. In power plants, turbines spin generators to produce electricity for entire cities. On a smaller scale, hand-crank generators can charge devices during emergencies. Even your car uses a generator called an alternator to keep the battery charged while the engine runs. These examples show how electromagnetic induction is woven into daily life. Transformers are devices that change the voltage of alternating current electricity. They use electromagnetic induction to transfer energy between two or more coils of wire called windings. By adjusting the number of coils in each winding, transformers can increase step-up or decrease step-down voltage. This ability is crucial for efficiently transmitting electricity over long distances and safely delivering it to homes and businesses. A transformer consists of a core, usually made of iron, and two sets of coils, the primary and secondary windings. The primary winding receives the input voltage, creating a changing magnetic field in the core. This field induces a voltage in the secondary winding, which delivers the output voltage. The ratio of coils between the windings determines whether the voltage is stepped up or down. An alternating current flows through the primary winding. It creates a changing magnetic field in the transformer's core. This changing field induces a voltage in the secondary winding through electromagnetic induction. If the secondary has more coils than the primary, the voltage increases. If fewer, the voltage decreases. This process allows electricity to be transmitted efficiently and safely across the power grid. Step-up transformers increase voltage for long-distance transmission, reducing energy loss. Step-down transformers decrease voltage for safe use in homes and businesses. Both types use the same principle, electromagnetic induction between coils. By carefully choosing the number of coils in each winding, engineers can control the voltage to match the needs of the electrical system. Transformers only work with alternating current because AC creates the changing magnetic field needed for induction. Direct current, which flows steadily in one direction, doesn't produce the necessary fluctuations. This is why our power grids use AC electricity, allowing transformers to efficiently step voltage up and down as needed. Core of a transformer is typically made from laminated iron to efficiently channel the magnetic field between the windings. This design minimizes energy loss and ensures that most of the magnetic field links the primary and secondary coils. The core's shape and material are carefully chosen to maximize efficiency and performance in real-world applications. Transformers are essential for modern power grids. High-voltage transmission lines carry electricity over long distances with minimal loss thanks to step-up transformers. Near cities and neighborhoods, step-down transformers reduce the voltage to safe levels for homes and businesses. Without transformers, it would be impossible to efficiently deliver electricity from power plants to end users. Electromagnetic induction isn't just for power plants and transformers, it's present in many everyday devices. Induction cooktops heat pots without flames, electric toothbrushes charge wirelessly, and even some trains use induction for contactless power transfer. This principle is woven into the fabric of modern technology, making our lives more convenient and efficient. Wireless charging uses electromagnetic induction to transfer energy from a charging pad to a device without physical contact. The charging pad contains a coil that creates a changing magnetic field when powered. The device has a matching coil that picks up this field, inducing a current that charges the battery. This technology is becoming increasingly common in smartphones and other portable electronics. Induction cooktops use electromagnetic induction to heat pots and pans directly. When the cooktop is turned on, it creates a changing magnetic field that induces electric currents in the metal cookware. These currents generate heat, cooking the food efficiently and safely. Induction cooking is faster and more energy efficient than traditional methods, with precise temperature control. Many electric toothbrushes use electromagnetic induction for wireless charging. The charging base contains a coil that generates a magnetic field when plugged in. The toothbrush has a coil inside that picks up this field, inducing a current to recharge the battery. This design keeps the toothbrush waterproof and safe for bathroom use. Maglev or magnetic levitation, trains use electromagnetic induction to float above the tracks and move at high speeds. Powerful magnets and coils create changing magnetic fields that lift and propel the train. This technology reduces friction, allowing for smooth, fast, and quiet transportation. Maglev trains are a prime example of induction in large-scale engineering. Electric guitars use electromagnetic induction in their pickups to convert string vibrations into electrical signals. When a metal string vibrates near a magnet wrapped with a coil of wire, it changes the magnetic field, inducing a current. This current is then amplified and turned into sound, giving electric guitars their distinctive tone. Dynamic microphones use electromagnetic induction to turn sound waves into electrical signals. Inside the microphone, a diaphragm moves in response to sound, moving a coil within a magnetic field. This movement induces a current that mirrors the sound wave, allowing voices and instruments to be recorded or amplified. Many credit card readers use electromagnetic induction to read data from the magnetic stripe. When you swipe your card, the reader's coil detects the changing magnetic field from the stripe, inducing a current that carries the card's information. This quick and reliable process is a practical application of induction in everyday transactions. Induction motors are widely used in appliances and industry. They work by passing AC through coils in the stator, creating a rotating magnetic field. This field induces a current in the rotor, causing it to spin. Induction motors are efficient, reliable, and essential for everything from fans to factory machines. The transmission of electricity over long distances relies on electromagnetic induction. High-voltage lines carry power from generators to transformers, which step the voltage up or down as needed. This system ensures efficient delivery of electricity to cities, factories, and homes, minimizing energy loss along the way. One challenge in power transmission is energy loss due to resistance in wires. By using transformers to increase voltage, the current is reduced, which minimizes these losses. This clever use of electromagnetic induction allows us to deliver electricity efficiently over vast distances, making modern power grids possible. Transformers also play a crucial role in electrical safety. By stepping voltage down before electricity enters homes, they reduce the risk of dangerous shocks and equipment damage. Proper grounding and insulation combined with transformer design help keep our electrical systems safe and reliable. Medical devices also use electromagnetic induction. MRI machines, for example, use powerful magnets and changing magnetic fields to create detailed images of the body. Induction is also used in wireless charging for medical implants and in some types of therapeutic equipment, highlighting its versatility beyond power generation. Scientists use electromagnetic induction in research to study materials, measure magnetic fields, and develop new technologies. Induction coils are used in experiments to generate and detect magnetic fields, helping researchers understand the properties of different substances and design innovative devices. Renewable energy sources like wind and hydropower rely on electromagnetic induction. Wind turbines and hydroelectric generators use spinning rotors and magnetic fields to generate electricity without burning fossil fuels. This clean energy production is essential for a sustainable future and demonstrates the ongoing importance of induction. Electric vehicles, EVs, use induction motors for propulsion and sometimes for wireless charging. These motors are efficient and require less maintenance than traditional engines. Inductive charging pads are being developed for public spaces, allowing EVs to charge without plugging in, making transportation cleaner and more convenient. Smart grids use advanced transformers and sensors based on electromagnetic induction to monitor and manage electricity flow. These systems can quickly respond to changes in demand, integrate renewable energy sources, and improve reliability. Induction technology is central to making power distribution smarter and more efficient. Despite its many benefits, electromagnetic induction faces challenges. Energy loss due to heat, the need for high-quality materials, and electromagnetic interference can affect performance. Engineers continually work to improve efficiency, reduce losses, and develop new materials to overcome these obstacles and expand the use of induction. The future of electromagnetic induction is bright. Ongoing research is leading to more efficient generators, smarter transformers, and new applications in wireless power transfer. As technology advances, induction will play an even greater role in sustainable energy, transportation, and everyday life. Let's recap the key concepts we've covered. Electromagnetic induction is the process of generating voltage by changing magnetic fields. It's the principle behind generators which produce electricity and transformers which adjust voltage for efficient transmission. This technology powers our homes, enables wireless charging, and drives innovation in many fields. Electromagnetic induction is fundamental to modern life. Without it, we wouldn't have reliable electricity, efficient power grids, or many of the conveniences we take for granted. Its applications span from massive power plants to tiny electronic devices, making it one of the most important discoveries in science and engineering. Generators use electromagnetic induction to convert mechanical energy into electrical energy. By spinning coils in magnetic fields, they produce the electricity that powers everything from cities to portable devices. Understanding how generators work helps us appreciate the complexity and reliability of our electrical systems. Transformers use electromagnetic induction to change voltage levels, making electricity transmission efficient and safe. By transferring energy between coils, they step voltage up for long-distance travel and down for local use. This technology is vital for delivering power to homes and businesses around the world. At its core, electromagnetic induction is about the relationship between electricity and magnetism. Changing one creates the other, allowing us to generate, transmit, and use electrical energy in countless ways. This interplay is the foundation of much of our modern technology and continues to inspire new inventions. From charging your phone wirelessly to riding a high-speed train, electromagnetic induction touches your life every day. Its applications are diverse, making technology more convenient, efficient, and accessible. As we continue to innovate, induction will remain a driving force behind new solutions and smarter devices. As we look to the future, electromagnetic induction will play a key role in sustainable energy, smart cities, and advanced transportation. Ongoing research and development promise even more efficient and versatile uses, ensuring that this principle remains at the heart of technological progress. Summary: electromagnetic induction is a powerful and versatile phenomenon that underpins much of our modern world. From generating and transmitting electricity to enabling wireless technologies and medical advances, its impact is vast. By understanding how it works, we can better appreciate the technology that powers our daily lives and look forward to even greater innovations in the future. Thank you for joining us on this journey through electromagnetic induction. We hope you now have a clearer understanding of how generators and transformers work and how this remarkable principle shapes the world around us. Stay curious and keep exploring the wonders of science and technology.